10 years ago, a spacecraft the size of a grand piano gave humanity its first real look at Pluto, and the images it sent back rewrote almost everything scientists thought they understood about that distant little world. And then, nothing. No follow-up mission, no orbiter, no lander, not even a formal plan on the books to go back. If Pluto turned out to be this fascinating, why did NASA seemingly just walk away? Stick around, because I'm going to walk you through the real, documented reasons NASA hasn't sent another mission to Pluto, and why the answer has almost nothing to do with a lack of scientific interest. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the far edge of our solar system. To understand why going back to Pluto is so difficult, you first have to understand just how difficult it was to get there even once. The mission that finally reached Pluto, called New Horizons, didn't happen quickly or easily. According to the mission's own principal investigator, Alan Stern, the path from the first serious mission proposal to an actual funded, launched spacecraft took 14 years, stretching from 1989 all the way to 2003, and it required roughly a dozen separate mission concepts to be proposed, studied, and in most cases rejected before one finally survived the process. It also took the full institutional weight of NASA's first official planetary science Decadal Survey, a report produced roughly once every 10 years by the national academies that essentially tells NASA which missions the broader scientific community considers the highest priority for the coming decade, to finally unlock the funding needed to move forward. Even after New Horizons was formally selected, the team had only about 4 years to design, build, and rigorously test an entirely new spacecraft, racing against a strict launch window in 2006. That was necessary to use Jupiter's gravity for a critical speed boost on the way out. Miss that window and the mission would have needed years of additional travel time, or possibly wouldn't have been approved to fly at all. That process alone tells you something important about how NASA actually decides where to send spacecraft. It isn't a single administrator picking a favorite destination. Every major planetary mission has to survive years of scientific review, cost analysis, and competition against every other proposed mission across the entire solar system before it ever gets anywhere near an actual launch pad. And once New Horizons was finally approved and built, it then had to survive a 9.5-year journey across billions of miles of empty space just to reach its target, arriving in July of 2015. That's the first major reason a return mission is so complicated. Whatever gets approved next has to survive that same brutal gauntlet all over again, starting essentially from scratch. It's worth remembering just how uncertain even New Horizons' own funding was, right up until the moment it actually flew. The mission was initially selected for funding back in 2001, only to be excluded entirely from NASA's proposed budget just 2 years later, in 2003. It took the mission being explicitly named as a top priority in that era's Planetary Science Decadal Survey, the report covering 2003 through 2013, to get funding reinstated and the project back on track. Even after the historic flyby succeeded in July of 2015, NASA officials told a congressional hearing that same summer that the agency still didn't have enough money to properly analyze the enormous volume of data New Horizons had sent back, since the full download from the spacecraft alone was expected to take up to 16 months to complete, given the incredibly slow data rates possible across such an enormous distance. In other words, even the mission, widely regarded as one of NASA's most successful planetary science achievements in decades, spent much of its life fighting for the basic funding needed just to happen, and just to be properly studied once it did. Here's the part that surprises a lot of people once they understand it. It's not that scientists lost interest in Pluto after New Horizons flew by. If anything, the opposite happened. According to planetary scientists who've studied the flyby data extensively, many of the biggest mysteries New Horizons actually uncovered can't be properly answered with the same kind of spacecraft that found them in the first place. New Horizons was built and equipped specifically for a fast flyby, a single narrow window of a few hours, to gather as much data as possible before continuing on into the Kuiper Belt forever. That kind of mission design is fantastic for capturing a first broad look at an entirely unexplored world, but it's fundamentally limited in what it can actually accomplish. A huge portion of Pluto and its system of 5 moons simply couldn't be mapped in enough detail during a single fast pass, since the spacecraft only had a good close view of one hemisphere as it flew through. Pluto's surface and atmosphere are also actively changing over time, evolving with the dwarf planet's extremely long elliptical 248-year orbit around the Sun, which means a single flyby captured only one brief snapshot of a world that keeps changing after the spacecraft moved on. And many of the specific mysteries New Horizons found, the geologically young ice plains, the possible buried ocean, the mysterious ice volcanoes, require entirely different scientific instruments than what New Horizons happened to carry. Instruments built to study exactly the kinds of features nobody knew to look for until after the flyby had already happened. If you're finding this as frustrating as a lot of planetary scientists clearly do, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. Because of all this, researchers at the Southwest Research Institute, the same organization behind New Horizons, have spent years actively developing and refining a serious proposal for a Pluto orbiter, a completely different kind of mission that would fly out to Pluto and then settle into orbit around it for an extended stay, rather than simply racing past. Led by Alan Stern and colleague Carly Howitt, these researchers have shown, using existing propulsion technology and realistic launch vehicles, that a mission concept could actually orbit the Pluto system for roughly 2 full years, gathering the kind of comprehensive, long-duration data a flyby could never provide. Some versions of the concept go even further, proposing that after finishing its primary tour of Pluto and its moons, the spacecraft could use a gravity assist from Pluto's large companion moon, Charon, to break out of orbit entirely and continue deeper into the Kuiper Belt, potentially visiting 1 or 2 additional Kuiper Belt objects, including another dwarf planet, for direct comparison. NASA has funded preliminary studies into this exact concept more than once, treating it as one of roughly 10 to 11 serious mission studies commissioned specifically to inform the scientific community's priorities heading into the next Decadal Survey. The technical case behind this orbiter concept is more solid than a lot of people might assume for a mission this far from the Sun. According to the research team's own published statements, an earlier study, funded directly by the Southwest Research Institute before NASA's own funding came through, had already demonstrated that a full orbital tour of the Pluto system was achievable using planned capability launch vehicles combined with existing electric propulsion systems, technology that already exists today, rather than something that would need to be invented from scratch. That distinction matters enormously in how these proposals get evaluated, because a mission relying on unproven or still theoretical technology carries far more financial and schedule risk than one built around hardware and propulsion methods that have already been tested and flown. The Pluto orbiter concept, in that specific sense, was never really the problem. The problem has always been finding room for it in a budget already stretched between several other equally credible destinations. And this is where the story runs into the real obstacle, because a funded study is not remotely the same thing as a funded mission. Every 10 years, that planetary science decadal survey process forces NASA and the broader scientific community to make an extraordinarily difficult choice, ranking every proposed major mission across the entire solar system against a budget that can only support a small handful of truly large flagship-class projects at any given time. In the most recent survey, covering the years 2023 through 2032 and released in 2022, the committee evaluated 6 potential flagship-class missions from across the solar system, including concepts targeting Neptune and its moon Triton, Venus, and Jupiter's moon Europa, alongside the Pluto system. When the rankings came out, the committee's top recommendation went to an orbiter and atmospheric probe mission to Uranus, a planet that hasn't had a dedicated visit from any spacecraft since Voyager 2's brief flyby all the way back in 1986. Second place went to a proposed orbiter and lander mission to Saturn's icy moon Enceladus, chosen specifically because of strong evidence for a subsurface ocean and active water plumes that make it an especially compelling target in the search for life beyond Earth. Pluto, despite everything New Horizons uncovered, didn't make the cut as one of the 2 priority flagship missions. Part of the reasoning behind that decision came down to something surprisingly practical: comparative readiness. According to members of the Decadal Survey Committee, the Uranus mission was judged ready to begin immediately, since it wouldn't require any brand new technology to be developed first, an advantage that carried real weight when committee members were forced to choose between several genuinely compelling but similarly expensive proposals. A Pluto orbiter concept, while scientifically exciting, was competing directly against missions to worlds that had never been visited at all with a dedicated orbiter, or that showed direct evidence of conditions that could potentially support life, criteria that carried enormous weight in how the committee ultimately ranked its priorities. It's also worth understanding how genuinely difficult this specific ranking decision was for the committee involved. Robin Canup, who co-chaired the steering committee behind the 2022 Decadal Survey, described the process candidly, noting that the committee was essentially choosing among several missions that are, in her own words, fantastic missions in their own right. The committee didn't just evaluate Uranus, Enceladus, and a Pluto orbiter. It also seriously considered flagship-class concepts for landers on Jupiter's moon Europa and on Mercury, an ambitious orbiter and lander mission to Venus, and a mission to orbit Neptune while repeatedly flying past its large moon Triton. An independent cost assessment performed by the Aerospace Corporation even factored into these deliberations, ultimately helping convince the committee that the proposed Venus flagship mission, for instance, carried too much technical risk and expense relative to its scientific payoff compared to the alternatives. Every single one of these missions had passionate scientific advocates behind it, and only two could realistically make the final cut given NASA's projected budget. It's worth understanding just how much money and time we're actually talking about here, because the numbers involved put the difficulty of squeezing in a Pluto mission into real perspective. The two flagship missions, recommended by the previous Decadal Survey covering 2013 through 2022, were the Perseverance Mars rover, which ultimately cost about $2.7 billion, and the Europa Clipper mission, which came in around $4.25 billion. The newly recommended Uranus orbiter and probe carries an estimated price tag in the range of $4 billion on its own, while the Enceladus Orbilander, recommended right behind it, could cost roughly $5 billion if NASA ever secures enough funding to pursue it as a genuine second flagship mission. Even fully funding just the top priority Uranus mission has proven difficult. According to independent analysis from the Planetary Society, NASA's actual budget has consistently underfunded planetary exploration relative to what the Decadal Survey itself recommended, resulting in real delays across multiple missions already in development, including projects that were themselves priorities from the previous decade's survey. Squeezing in an entirely new additional flagship-class mission to Pluto on top of an Uranus mission, an Enceladus mission, and an ongoing Mars sample return campaign that's already straining the existing budget simply hasn't been realistic within any of NASA's actual funding projections. There's a second, more physical obstacle sitting underneath all of this budget pressure, and it affects every single outer solar system mission NASA might want to fly, not just Pluto. Spacecraft traveling this far from the sun receive far too little sunlight for standard solar panels to generate any meaningful power, which means missions to Pluto, Uranus, Enceladus, or anywhere else in the outer solar system depend instead on something called a radioisotope thermoelectric generator, a device that converts heat from the natural radioactive decay of a specific isotope of plutonium into usable electricity. The problem is that the United States effectively stopped producing new plutonium-238 for decades, and even though production has slowly restarted in more recent years, the total available global supply remains extremely limited. According to reporting connected directly to the Uranus orbiter and probe mission itself, NASA announced in 2023 that a shortfall specifically in plutonium production meant the mission's originally planned launch date needed to be pushed back from the early 2030s to somewhere in the mid to late 2030s instead. If the single highest priority flagship mission in the entire Decadal Survey is already being delayed because there isn't enough of this specific fuel to go around, that gives you a real sense of just how constrained the entire supply chain is for any additional outer solar system mission, Pluto included, that might try to compete for the same limited stockpile. This fuel constraint isn't a minor footnote either. It represents a genuinely hard physical limit that no amount of additional funding can immediately bypass, since simply throwing more money at the problem doesn't speed up a nuclear material production process that involves specialized reactors, complex processing facilities, and safety protocols that take years to scale up even under ideal circumstances. Every kilogram of plutonium-238 currently in the national stockpile has to be allocated across every single mission that needs it, whether that's a Mars rover, an outer planet flagship, or any future Pluto mission, which means proposals for additional distant destinations are effectively competing not just for dollars, but for a physical resource that simply cannot be manufactured on demand. Put all of these obstacles together and the picture becomes much clearer. It isn't that scientists stopped caring about Pluto after New Horizons. Serious, technically credible mission concepts for a Pluto orbiter exist right now, developed by the very same team that built New Horizons in the first place, and they've been formally studied and funded at the preliminary level more than once. What's missing isn't the idea. It's the combination of things every single outer solar system mission needs simultaneously in order to actually happen. A favorable ranking in an extraordinarily competitive, once-a-decade prioritization process, several $1 billion of sustained budget, commitment across more than a decade of development and travel time, and a large enough supply of an extremely scarce radioactive fuel source that NASA's own flagship priority mission is already struggling to secure enough of. Pluto lost that three-way competition this round, not because researchers gave up on it, but because Uranus and Enceladus each presented compelling cases of their own, and NASA's budget, by every independent analysis available, isn't currently large enough to fund all three. None of that means Pluto is permanently off the table. Decadal surveys happen roughly once every 10 years, and the next one, covering the years beyond 2032, will give the scientific community another full opportunity to reassess priorities based on whatever new evidence and mission concepts exist by then. If a Pluto orbiter, proposal survives to that point, and if either the Uranus or Enceladus missions currently ahead of it in line encounter unexpected roadblocks of their own, there's a real chance Pluto could move back up the list. Alan Stern and his colleagues have continued refining and publicizing the orbiter concept specifically to keep it ready and competitive whenever that next opportunity comes around, rather than letting the idea quietly disappear simply because it didn't win this particular round of an extraordinarily difficult prioritization process. In the meantime, New Horizons itself hasn't gone silent. After its historic flyby of Pluto, the spacecraft continued deeper into the Kuiper Belt and, in January of 2019, flew past a much smaller, more distant object nicknamed Arrokoth, becoming the most distant object ever explored up close by any spacecraft in history at the time. New Horizons remains healthy and still carries enough remaining fuel for potentially one more distant flyby target if NASA approves yet another mission extension down the road, meaning the very same spacecraft that first revealed Pluto's secrets a decade ago might still have a little more exploring left to do before its journey is finally done. There's a certain irony worth sitting with here, given how this whole story started. When NASA Administrator Jim Bridenstine spoke at the International Astronautical Congress back in 2019, he told the audience directly that, in his own personal view as the head of the agency, he believed Pluto should still be classified as a planet, pushing back against the International Astronomical Union's controversial 2006 reclassification. That comment captured something real about the mood inside NASA following New Horizons' success, a level of genuine institutional affection for this small, distant world that goes well beyond simple scientific curiosity. Losing out in a budget-driven ranking process isn't the same as losing that underlying enthusiasm, and it's part of why the orbiter concept has continued to be refined and reproposed rather than quietly shelved for good. So what does all of this actually add up to? NASA didn't abandon Pluto out of a lack of curiosity. A serious, technically sound proposal for a return mission exists right now, built by the same team responsible for the first mission's remarkable success, and it's been studied, funded at the preliminary level, and kept ready for exactly this kind of opportunity. What stands between that proposal and an actual launch pad is an extraordinarily difficult, once-a-decade competition against equally compelling missions to worlds like Uranus and Enceladus, a budget that even NASA's own top pick is struggling to fully secure, and a scarce radioactive fuel supply that every single outer solar system mission has to compete for. Pluto's story with NASA isn't over. It's simply waiting its turn in a line that's far longer and far more expensive than most people realize. If stories like this one, grounded in real published research and documented mission history rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because there's a real chance Pluto's turn comes back around sooner than anyone currently expects. Thanks for watching, and I'll see you in the next one.